To understand where KL divergence comes from, we look at cross-entropy. Cross-entropy is the total cost of using model Q to describe truth P. This total cost is made of two parts. First, entropy. This is fixed. The second part is the KL divergence. It is the extra cost or penalty for your model being different from the truth. As we move our model Q closer to P, the cross-entropy shrinks because the KL divergence vanishes. But the entropy of the truth remains. Mathematically, we are integrating the log ratio of P and Q, weighted by P itself. Let's visualize what this ratio means. At any point x, if P is higher than Q, the ratio is greater than 1, and the log is positive. This adds to our divergence. KL divergence is never negative. This is thanks to Jensen's inequality. Since the negative log function is convex, the average surprise is always greater than or equal to the surprise of the average. First, the optimal case. When our model Q perfectly matches reality P, the divergence is 0. Next, the biased case. A shift in the mean creates a gap. Notice the KL value rises as the overlap decreases. In the vague case, Q is too broad. It covers the truth but is inefficient, wasting information on unlikely events. Finally, the risky case. Q is too narrow. It ignores the possibilities that P says are likely. This is heavily punished. KL divergence is asymmetric. Using a wide model for a narrow truth feels different than using a narrow model for a wide truth. Because the ratio of P over Q is weighted by P, the penalty for missing information is much higher than the penalty for being too broad. Now, why does the order matter? Why is P parallel Q not the same as Q parallel P? In the left box, the truth P is broad, but our model Q is narrow. We are missing many likely events. This results in a massive penalty. But in the right box, if the truth P is narrow and our model Q is broad, the penalty is much smaller. Geometrically, KL divergence is weighted by the first distribution. It cares deeply about what you are missing, not just how far apart you are. This asymmetry is why KL divergence is a divergence, and not a distance. It depends on which distribution you define as the ground truth. In machine learning, the direction of KL matters. Forward KL, where we weight by P, forces the model to cover all modes of the truth. This is mean seeking. But reverse KL, weighting by the model Q, forces the model to pick just one mode and fit it perfectly. This is mode seeking. Let's summarize everything with this dashboard. Watch the KL value as we manipulate the model. As we move the mean towards 0, the divergence drops. But notice that if our sigma is too small, the KL divergence remains high because we are missing the truth's variance. When we match the truth exactly, the KL divergence vanishes. This is the goal of every optimization algorithm in AI.